Hi there, welcome to another video. Today we are looking at all things compression, why we use it, and the different types. So we are looking at compression, run length encoding, and something called Huffman encoding. Okay, so our key learning objectives today are understanding why we use compression, advantages and disadvantages of the two different types, so lossy and lossless, suggest where we would potentially use run length encoding, and also work out a Huffman encoded value and compare it against ASCII. So, okay, so when we talk about compression, if I said to you I was going to compress something, I'm normally going to make it smaller. So you can look at this example of a can underneath my picture. So if we were to compress a Coke can, we would squish that up until it is smaller in size. And that is what we do to data. Okay, so it's the process of encoding, modifying, or sort of removing data in order to reduce its size. There's two different types, lossy and lossless. So I'm going to take you through those types now. So you may have seen compression actually when you have gone to send an email from your phone, or maybe you've seen something like a zip file. So the idea of both of these types of compression is to obviously make that file smaller, because potentially if we're sending a smaller file size, the data transmission time is also going to be reduced. You also might have sort of a storage limit, the size that a file can be. And you can take a little look at my example here. We can see the actual size is 424 kilobytes, but we can compress that image right down to 29.5. Okay, so you could make the decision on whether you wanted to reduce quality for a faster transmission size, or maybe haven't got enough storage. It's all those sorts of compromises when it comes to compression. So, when we talk about lossy compression, it is a form of compression that literally just removes the data. We can't get it back at a later point, and we often see this in sort of images and in videos. So let's take this example I had earlier, and I chose to send it in a smaller version, so the 29.5 kilobytes. Well, this is a picture of my dog Lenny. We can see here the image quality has actually reduced. So when I compare that, okay, so I've just moved my camera so you can have a little look. If you look really closely, you can see on the left-hand side, this smaller version is actually slightly more pixelated. Now, not too much, but we have lost details such as maybe a little bit of sort of his snout becomes a little bit more pixelated, a little bit more blurry looking. And this is exactly what compression does. It basically is removing the amount of pixels available to represent the different colours. So we're actually reducing the colour depth here. You can see again on his teeth, on the right hand side, they are slightly clearer. So lossy compression is really important that you understand. It removes data and in turn reducing the file size. You cannot get that back later. It's typically sort of used within images, because you may not notice, you may not need that level of data. However, it wouldn't be suitable for a text file, because if you randomly removed sort of characters in a text file, perhaps the sort of data wouldn't really make sense. Just another example of lossy and compression. On the right hand side, we can see our smaller image. So you can see this maybe in the wing, lacking clarity, where this one is much more detailed. We can see quite a few sort of little pixels here that are maybe starting to not look as clear. So again, like I say, it is just down to why you need that image. Okay, so now we're moving on to lossless compression. You have probably seen this when it comes to sort of zip files. So you may have seen something sort of saying zip file or extract all, and all that does is it sort of uses an algorithm to reduce the file size. The important thing about lossless compression is we can get that level of detail back later. So we can decompress it without any reduction in quality. Okay, so just to recap, lossy compression is really useful for things like images, videos, things where we want to sort of compromise with maybe the quality that we're seeing. It removes the data and you can no longer get that quality back. It is removed, that is it. Okay, so lossless compression, you can reduce the data, however, you can decompress it again with no impact or little impact to the quality of the data. So we are going to look at two forms of lossless compression, run length encoding and Huffman encoding. So first up, we're looking at run length encoding. So it's a compression algorithm, and basically it's going to compare consecutive runs of the same data. So two pieces of data that are the same. Okay, so we would potentially say one white, two yellow, two white, two black. So what I'm doing is I'm technically compressing that data. However, this is a bit of an issue with run length encoding. If there are, for example, lots and lots of changes, are we actually making that data smaller? So this has 1, 2, 3, 4, 5, 6, 7 different values here. Okay, so this has 7 different values here. However, if I had just written white, yellow, yellow, white, white, black, black, actually we have used less characters than what we have for the run length encoding. So this is quite an issue. If you do not have the same characters in long sort of sequences, long runs, it can actually be not much of a compression algorithm at all. Actually, sort of see that potentially not much reduction in the data is sort of carried out. Okay, so this sort of brings me to my next point. That's only really useful if there's long runs of consecutive pairs. That is the issue. So if I, again, were to sort of compress this data, I might not see much in the form of compression or reduction in file size. So one white, one blue, one red, one blue. Now there's not any sort of similar values here, the same values. So we're seeing, actually, we're adding data at this point where we could have just put white, blue, red, blue, red, white, purple. Yeah, and actually I've used an extra character every single time. Okay, so we've talked about run length encoding. It is literally just counting consecutive pairs next to each other. Okay, so here is a typical exam question. I'll let you have a read, have a little pause of this video and see if you can attempt it. We're going to run through this in just a moment. Okay, so to get my 2 marks, obviously I want to mention the fact that it's not really compressed that data at all. There's no real reduction in file size because there are not very many consecutive pairs that I can group together. So this was my answer, worth 2 marks out of 2. The image has a low number of consecutive repeating colours. The compressed data will take up more storage space than the original image. And that will get you 2 marks. Obviously, first mark for saying low number of consecutive values, or in this case, I talked about repeating colours. And the second mark is when you are actually mentioning it may take up more storage space. Okay, next that we're going to look at is Huffman encoding. So it's a form of lossless compression again, and it encodes digital data or files without losing any data. So the way that it does this is it takes the most frequently used character in sort of whatever it's compressing, and it creates a sort of a Huffman tree based on this value. You need to be able to read and work out the difference sort of versus just storing something in ASCII. So normally what you get given is you get given the Huffman tree and sort of also a table to go along with it. So you can see if I want to represent the capital sort of uppercase A, it's going to be 1, 1. That's why you see that here. If I wanted to, for example, put the uppercase B, it's going to be 1 and then 0. So towards the left is going to be 1, towards the right is 0, and that's all you are doing. Okay, if you have ever used a Morse code tree, it is a similar thing. Okay, so I'm going to go through sort of this example first, and then I'm going to give you a question in just a moment. So what I also need you to know is if I was representing a value like this in ASCII, so BADEC, we need to remember that ASCII sort of requires 7 bits per character. So if you are unsure what ASCII is, I suggest you go to sort of one of my videos on character encoding. But just for now, I need you to understand that sort of it's a minimum of 7 bits per character is used without it being compressed. So the value B, if we work this one out, we're going to go 1, 0. So 1, 0. A is 1, 1. And we can actually just use this table if we like. It depends on what you prefer doing. D is 0, 0, 1. Now I can double check this. 0, 0, 1. E is 0, 0, 0. And C again is 0, 1. So the amount of bits this has taken to represent this sort of sequence of characters is, and we're literally just going to count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it has taken 12 bits to represent these characters using Huffman encoding. It is as simple as that. You are just working out the bits and then you're going to count them. So just to compare this to ASCII, so BADEC, ASCII requires 7 bits for every single character that it can support. So what calculation we're going to do here is 1, 2, 3, 4, 5. 5 times 7 bits, so a minimum of 7 bits per character. That is going to give us a total of 35 bits without it being compressed. Using Huffman encoding, we can represent the same sort of characters with only 12 bits. Okay, so I'd like you to pause the video now and see if you can fill in this table. Okay, so I'm just going to run through it. Huffman encoding, all I'm going to do is look at this table here just for ease. So B is 1, 0. A is 1, 1. A is 1, 1. C is 0, 1. D is 0, 0, 1. E is 0, 0, 0. How many bits is required? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 bits. The amount of ASCII bits required are, well, there is 1, 2, 3, 4, 5, 6. 6 times 7 is 42 bits required ASCII. The total saving in bits using Huffman encoding, we're going to take 14 away from 42, is 28. So we have saved 28 bits just by using Huffman encoding. Okay, final one. Give the video a pause, give it a read, and see if you can answer this question for 3 marks. Off you go. Okay, so here is my answer. I'm just going to show you where you get the 3 marks. So you get 1 mark for correctly working out the Huffman sort of value. A tip I would sort of suggest for your exam is literally write everything down, make sure it's as clear as possible. So you can see I have worked out 10 bits and I've even written Huffman next to it because I want to make sure that examiner is finding it easy to give me marks. It's really important that you keep that in mind. Is this clear? Is this going to get me the most amount of marks? The next thing, again, I'm making it really easy for that examiner to give me marks. ASCII, we know is 7 bits per character. We have 4 characters here, so A, C, E, D. And all I am going to do is times 4 by 7. I get 28 as a value. And then I know in my head 10 minus 28. However, I'm going to make it really, really clear again for the examiner so I get my third mark. So that is 1, 2, 3 marks out of 3. Thanks for watching this video. Hopefully you found it useful. See you in another one.